Hi. By this time you are all familiar with the Maxwell's relations in thermodynamics, the set of four equations which is of great relevance in studying various thermodynamical systems. And during the discussion of the significance of these relationships, we have seen that they are particularly useful in measuring quantities which are not directly measurable or which is hard to measure in terms of the easily measurable or easily accessible variables like pressure, volume and temperature. Moreover, these equations will be helping us various thermodynamical processes that usually occurs in various systems. Now, as some specific examples of the applications of Maxwell relations, we will discuss three different cases which are going to be useful. The three specific cases of applications as per your syllabus are TdS equations, Clausius-Clapeyron equation, and also the Joule-Thomson expansion. So these are three topics that we will discuss where we will be using Maxwell's relations to arrive at some useful conclusions. And we have seen that out of the four variables which are regarded as the natural variables like pressure, volume, temperature and entropy, pressure, volume and temperature are easily accessible and controllable, whereas the entropy of the system, which is an abstract concept, is not directly accessible or measurable. So in situations involving a change in entropy, we should devise some method by which we have to find out the change in entropy in terms of the other measurable quantities like pressure, volume and temperature. And for this we will be using a set of relations which are known as TdS equations. Similarly, whenever we discuss about phase changes which are introduced as first order phase transitions, for example conversion of liquid water into steam or conversion of ice into liquid water, where there involves some sort of a latent heat, then application of or the use of Maxwell relation results in another seminal equations in thermodynamics which is known as the Clausius-Clapeyron equation. Similarly, there are several phenomena in thermodynamics, and one such relevant phenomena is known as Joule-Thomson expansion. So in all the three topics that we are going to discuss in the coming sessions, we will see that we will be applying one or more Maxwell's relations to arrive at useful conclusions. And on the right side you can see some equations on the screen whose left side is all TdS, T multiplied by ds, and these three equations are usually referred to as the TdS equations in thermodynamics. There are three TdS equations which have been shown on the screen. So as per the syllabus, we are expected to learn about two of these TdS equations. We will be shortly deriving two of these relationships. We will explain what is the relevance of this relationship, and I leave the derivation of the third TdS equation as an assignment for you. So let's go to the first TdS equation and its derivation. See, let's first of all understand what is the relevance of TdS equations in thermodynamics. Even though the syllabus demands that these equations be discussed as an application of the Maxwell's relations, there is some sort of a relevance for the TdS equations. You know, as we have seen, entropy is such an abstract quantity which is not easily accessible or measurable. But we need to measure the changes in entropy in several thermodynamic phenomena, because entropy is such a function which can give you a lot of information regarding the stability of the system or regarding the equilibrium nature of the system. Hence, what we usually do is that we will be expressing entropy yes in terms of the other three natural variables. So you can express the entropy of a system or entropy change of a system, to be precise, in terms of the other three variables, natural variables. So I can express entropy as a function of, there are three different choices. So either I can express entropy as a function of volume and temperature, or I can express entropy as a function of pressure and temperature. These are all several options that is left. Or I can express entropy as a function of the other, what is the third pair that will be of, yeah, of course, I can take volume and pressure. So there are three options left for expressing entropy in terms of the other variables. So you can see that we will be able to obtain three separate relations for change in entropy. So if you are using this functional relationship between the variables, then you will be getting one equation for ds. If you express if you use this particular functional form of entropy, you will be getting another equation for ds, and the third equation will give you another expression for ds. Okay, so these equations, when you multiply with the temperature, it will give you three relations in terms of TdS, and we will see that the derivation of each of these relationship is quite resembling, and since it is having a resemblance, usually these TdS equations are commonly known among the students of thermodynamics as something what is known as TdS equations. But remember, TdS means something difficult, something tiresome. So, but we will see that it's quite easy if you understand what we are actually doing. Even though those equations look very similar, if you understand what is the use and what is the motivation in doing or in deriving such equations, it will be quite easy for you to remember even the equation or the derivation. So we'll do that starting from the first equations. So here we have got a definition for what is actually a TdS equation. So you'll see that, as I mentioned, it's a set of three equations. So there are three TdS equations commonly used in thermodynamics. So what is the use of that? It is useful in calculating the change in entropy of a system during various reversible processes. Okay, be careful about this one. The use of TdS equation, or why TdS equations were derived. The reason is that they are useful, or that enables us in calculating the change in entropy of a system. So the TdS equations are useful in calculating the change in entropy of a system. Why we are interested in a separate set of equation for calculating the change in entropy of the system? The reason should be well and clear, because as we mentioned earlier, entropy is such a quantity whose direct measurement is quite impossible or very difficult. Okay, since we do not have a direct access over entropy, we have to depend upon other related variables, so that, and the mathematical relations like TdS equation, so that you will be able to calculate the change in entropy of the system in going from initial state to the final state. Right? So this is the okay, these are the equations. Change in entropy of the system during, there are some restrictions on use of the equation because we have defined ds for reversible processes. That is one reason why these equations will enable us in calculating the change in entropy system during various reversible processes. It can be isobaric process, isochoric process, whatever it is. Okay, but the process should be inherently reversible in terms of either dV and dt. That's what I have told you. Either dV and dt, or dP and dt, or dV and dP. So there are three choices left. So each of these choices will give you one TdS equation. That's why I told you there are altogether three TdS equations, but your syllabus and your textbook will be discussing only two. So never think that it's only two. Actually, there are three. Okay, or see, this is one choice, or you can express the change in entropy of the system in terms of directly measurable quantities, such as there are some other directly measurable quantities for system. That is, one thing is bulk modulus of the substance can be calculated. It can be directly experimentally measured. Bulk modulus, like you are measuring the Young's modulus of a solid substance in your labs. Okay, using the bending experiments, you are measuring the Young's modulus. Similarly, there are methods by which you can calculate the bulk modulus of the material, or okay, see, there is a correction, or the coefficient of expansion. So you just heat a substance, you measure what is the change in volume of the substance, and from that you can compare with the original volume. You will be able to get what is known as the coefficient of expansion of the material. So these properties, okay, by measuring these properties and using the relation of these properties with what? Just the change in entropy of the system, using Maxwell's relation, and by using proper integration, you will be able to calculate the change in entropy of the system during a process. Okay, so that is the ultimate aim of deriving this set of three equations using Maxwell's relation. And we will see that in the derivation of each of this TdS equation, we will be using one Maxwell relation or the other. So we will see that how to decide which equation to be used. That actually it will come on the way. So let's start by discussing the first TdS equation. So to discuss the first TdS equation, let's begin like this. As I told you, the entropy of a pure substance can be considered as a function of any two of the three variables, namely the pressure, volume, and temperature. Now let us take the first choice. If remember, we are taking a pure substance, if S is a function of V and T. So I'm taking the first choice. This is the first choice for me, and the first choice will give you the first TdS equation. If S is equal to S of V comma T, right? Means if you are able to express the entropy of the system in terms of the volume of the system and the temperature what you are applying to the system. Okay. Now, can you just express the differential change in S? So therefore, ds will be equal to, what will be ds equal to? Just follow the mathematics of partial derivatives. So ds will be equal to dou s. You are quite familiar with all these techniques by the time, thermodynamics, and I think by the time you have noted that in order to master thermodynamic concepts, you need to master only one technique in mathematics. That is the technique of differentiation, or precisely partial derivatives. If you are comfortable with the technique of partial derivatives and its meaning, then it's quite easy. Any student who has got a conceptual clarity in the fundamentals of thermodynamics will be able to master the subject. Okay, so hope that you are feeling comfortable by the time. So dou s by dou v, right, at constant temperature, right, times dv is not the thing, plus dou s by dou t at constant volume times dt. So this is the result. You know what's the meaning of this one? We have already mentioned about what are the meanings of such relationships. It's the change in entropy. It's the infinitesimal change in entropy for a system due to an infinitesimal change in the volume of the system dV and an infinitesimal change in the temperature of the system dt occurring simultaneously. First term corresponds to the change in entropy due to change in volume, and the second term represents the change in entropy due to change in temperature. So there are two reasons by which the entropy can change if S is a function of V and T. That's mathematical meaning. Okay, just have that idea. Now see, it's ds here, right? So let's see. So it's ds here. So this is, let me call that this is equation number 1. Now what I'm doing, just let me multiply by t throughout. I'm multiplying by t throughout, and you will understand why I'm going to multiply by t throughout. Okay, so multiplying by t, so what will be the equation? It becomes TdS, and that is the way in which you will be getting the first TdS equation. So LHS is TdS, right? So the first TdS equation, TdS. So on the right side also you'll be getting. So let me do one thing. I'm just writing the second term in equation number 1 as the first term for some reason, for some symmetry purpose. Okay, so t into the bracket is there, dou s, t into dou s by dou t at v times dt plus, right? Similarly, t into the first term there, I am writing a second. I could have done it, this particular step I could have done in the first equation itself, but okay, I have begun some reason. So dou s by dou v at t dv. I think I haven't missed anything. So I have multiplied by t. Therefore, multiplying by t, this is what happened. Now, since I need to get a TdS equation, let me keep the TdS on the left side as such. I'm not going to modify it. But on the right side, I have some chance. On the right side, I have some chance. Okay. See what I'm doing. Can you see that the first equation? So don't you know that for a reversible process, you can write what is the definition of this ds. So the definition of ds for a reversible process is, for any reversible process in general, is ds is equal to d bar q over t, where this d bar q is the d bar q r. We do not write it explicitly, right? So now if I'm considering a reversible isochoric process, so this is general equation that we write. So if we are considering a reversible isochoric process, what modification I have to write? So you know that you are specifying that it should be an isochoric process, means the volume should be constant. So instead of writing ds, I'll be better writing as the what? Dou s. Instead of writing ds, I'll be writing it as what? Dou s. So for a reversible isochoric process, you will understand why I am interested in such process. Isochoric process, I can rewrite this equation, modify this equation as, instead of ds, I'll be writing dou s, and dou shows that I'm just taking the change in entropy under particular something remaining constant, that is volume is remaining constant. So dou s, in order to differentiate it, let me write as some dou bar q, okay, over t is the the temperature. Okay, so dou s will be equal to dou bar q by t, or what I can do is that in this case I can write t dou s is equal to d bar q. T dou s is equal to d bar q. So this is the equation that I have to apply for a reversible isochoric process. So for a reversible isochoric process, so you can just add that condition here. I will write TdS is equal to, can you see here, T dou s here, okay, T dou s is seen here, right, and that is for V at constant volume. So I can replace that one by what? D bar q. So I am replacing T dou s in the numerator as D bar q over dou t, dou bar q by dou t, okay, at constant volume, that is there, times dt plus the second term I am keeping as such, okay, for the time being, plus t. I can do some changes here, but I am retaining it as so that we are able to write it, dou s by dou v at t times dv. Let me retain it like this. So this is equation number 2 for the time being. You can give some equation numbers as per your like. I'm just giving it so that I can give a pause. Now, two things. What is dq by dt or dou q by dou t at v? Can you recall what is this one? And if you can memorize, you will see that dq or dou q by dou t at constant volume was nothing but the definition for heat capacity at constant volume for the system. CV, capital CV, dou Q by dou T at V, we have seen that, and that is equal to, right, dou U by dou T at, okay, we have seen that, okay, CV. So dou Q by dou T at V is CV, that's one thing. So what I will do is that I will rewrite this term as CV. This is CV, so that is what, CV dt. CV dt, first term is modified. Now second term, let me put up okay, yes, plus or minus, let's check it. Now see, what we have done here is that see, you look at this equation here, left side you had ds, right side also, here you had a dou s term, here also you had a dou s term, but you know your aim is to finally calculate what is S, what is entropy, but you cannot have, or you cannot use an equation for one unknown where both the right side also is having what, same unknown. Okay, you want to find out x. So if you have what, ax plus bx like this, no, okay, if you have some terms in x, whatever it is, whatever be, whether it's a differential equation or any other equation, you know, okay, you can see that either you have to collect all the x, okay, so maybe this is x dash, right, this is x double dash, like that, some derivatives. So that's a problem, or that is why we are just changing this dou s in terms of dou bar q, and you can calculate dou bar q easily, or you can calculate CV of the substances equally. Okay, so you just substituted for the ds term in the first term by CV. That is the ultimate thing what has happened. But still there is a problem with the second term. Why? Because here you have got dou s by dou v, right? Still this dou s is remaining on the right side. So what you should do? Okay, see, how do we begin our topic? Always remember how to begin our topic. The concept of TdS equations we have introduced by telling that that is an application of the Maxwell's relations. Okay, so TdS equations we are deriving by using Maxwell relations. So the scope remains there. What is that? Can't you use Maxwell's relations here to get rid of dou s by dou v? Because you remember the basic idea of Maxwell relation, the significance of Maxwell relation was to express unknown quantities or difficult to measure or hard to measure quantities in terms of known quantities. So let's use Maxwell relation here. So what is dou s by dou v? Let's write it like this. Okay, you know how to recall it. Dou s by dou v. Okay, at constant what? At constant t. Just verify is not of the form of Maxwell relation one side, and you know what to, how to write the other side. What will be the right other side? Can you recall it? I give some time for you to predict what will be the right side of this equation without referring. What will be the right side? Okay, you know the technique. What is that? The cross multiplication should give you the dimensions of energy, or it should give you the conjugate pairs. So what is that? Here V in the denominator, so here it should be P. So I'll be writing dou P. Here S in the numerator on left side, so the denominator should be T. So dou P by dou T, it's gone. Okay, dou P by dou T, it's over. And now what should be kept as a constant? Here you can see that T is kept a constant on the LHS. Okay, and what is the relation of T with the numerator? S is there in the numerator here, and T is the conjugate variable of S. So what should be kept a constant on the other side? It should be the conjugate variable of pressure. And what's the conjugate variable of pressure? That is volume. So V is the constant. Now one more thing you have to do. What is that? You have to memorize, or you have to make sure whether it is a plus equation or a minus equation. And that technique also I had mentioned. How to remember? Several ways. But one easy technique is that whenever P and T are coming on the same side, either in the numerator or the denominator, that equations, those, there will be two such equations with the P and T coming in the numerator and denominator on the same side. Those two equations are positive. Memorize it. Okay, so certainly this equation will be positive. Now can you substitute this equation? So I am substituting this equation and this equation. This is from Maxwell's equation. So I think we introduced this one as the third Maxwell's equation. Okay, so you can just mention it from the third Maxwell's equations. See, Maxwell's equation, third Maxwell's equation. when you make notes, see that you add something. So whatever I am telling, see, I'm explaining, see the motivation behind introducing the things. When you do it, see that within 1 minute this derivation will be over. Okay, so for pedagogical reasons, so that you remember why each step is written, I'm just explaining the things in detail. Okay, if you feel it is too lengthy, you can just increase the speed, please. Okay, depending on whatever you feel like. See, so what I'm doing, I'm substituting for the term. So plus t into, instead of dou s by dou v, what I am supposed to substitute? I'm supposed to substitute dou p over dou t at constant volume. Do not miss out anything. dv. Now on the left side, what do you have? You have got TdS. Now you have got an equation where the left side is TdS and the right side do not have any S term. So Cv, a measurable quantity. Change in temperature can be easily measured using thermometers. Dou P, change in pressure, can be calculated by barometer measurements. Pressure gauges. Dou T can be measured, dV can be measured. So you can see on the right side, all the quantities are experimentally measurable or accessible quantities. And on the left side, you have got the temperature of the system. Okay, so TdS, it's there. So if you integrate the left side, okay, within proper limits, automatically you will be getting the change in entropy of the system in going from the initial state to the final state. Okay, so this equation which we have arrived now is known as the first TdS equation in thermodynamics. Okay, and that, as per the definition we have had, can be used to calculate the change in entropy of the system in terms of dV and dt. In terms of dV and dt, can you see dV here and dt here? Okay, so if you try to remember these equations well and good, otherwise you should be able to derive it within 2 or 3 steps. Within 1 minute you will be able to complete it. Okay, so try to understand that what we have done, what was the motivation behind, what was the logic behind the derivation. Always remember, you started by expressing S as a function of volume and temperature. Then you took ds for an infinitesimal process by the chain rule in partial derivative. Then each term was having ds or dou s, which you had to replace. So one of the term you replace by multiplying with t and changing it to Cv, and the other term you replace by using one of the relevant Maxwell's relations, and finally you obtained the RHS equation, which is devoid of what? The dou s term, and all the terms were measurable quantities. So by integrating this equation, you'll be able to calculate the change in entropy of the system. So this is the first TdS equation in thermodynamics. Hope you could follow me. Right? Now, once you understood this one, okay, within minimum time, you can derive the second TdS equation or third TdS equation by yourself. So, but for completeness, let me do the second TdS equation also. Okay, so you know what we are going to do. So we are going to take the second functional dependence of entropy, right? So let's go to the next screen. Second TdS equation. You know where you will begin with. Okay, so what you do? If you can study yourself, it's the same pattern. Okay, so it will be a practice for you. If S is equal to S of PT, let me write the other way, S of TP, both are same, you know, but it will help me to reduce one step. If S is expressed as a function of temperature and pressure of the system, that's all. Okay, therefore for any infinitesimal process, the change in entropy of the system is represented by the total differential ds. So dou s will be equal to, ds will be equal to dou s by dou t at constant pressure times dt plus dou s with respect to dou p at constant temperature times dp, right? So that is the first relevant equation. Now you know what to do. What did you do there in the first TdS equation? You multiplied throughout by T, because anyway you have to get TdS on the left side. Okay, so multiplying by T throughout. You can skip these steps, but I'm just writing it. Throughout, what do you get? You get TdS is equal to T into dou S by dou T at constant pressure times dt plus T into dou S by dou P at constant temperature times dP. That's your second equation. Now what do you do? You are going to make some modifications. What is the modification? Here, can't you see T into dou S? So for a reversible, here see the pressure is kept a constant. So what type of process? Isobaric process. Instead of isochoric process that we have done, used to derive the first TdS equation, here we are taking a reversible isobaric process. The reason is well and clear, because you have the quantity at constant P. What is what you can say? I can say the T into dou S will be equal to dou bar Q. T into dou S is equal to dou bar Q. This dou bar I am using okay, because we have been using inexact differentials by dou bar or d bar Q. Okay, partial derivative, that's all. So what will be the equation number 2 becoming? Right? So I can write, therefore TdS is equal to, you can skip many of these steps, but I'm doing it for clarity. Okay, so it will be dou bar Q over dou T at constant pressure times dt, right? So sorry, yeah, that's okay. Then plus T into, no change now for the second term in this step, I'm not doing anything now. T into dou S by dou P at T times what? dP. Let me call this one as equation number 3. Right? Now we have to see, okay, what is dou Q by dou T at P? Dou Q by dou T at P is nothing, you are Cp, right? The definition of heat capacity at constant pressure. Okay, so it will be Cp dt. Now, here again there is an S term, but I have to get rid of S term. So far we didn't use our, what do you say, okay, lifeline. What is the lifeline? You can use one Maxwell relation. That's the lifeline here in the derivation. So let's use the lifeline. What's the lifeline? So I have to replace dou S by dou P at constant T somehow, so that I get rid of S. Please apply the technique and predict what will be the equation. Just practice it, please. Whenever you get a chance, practice writing or predicting the Maxwell's relations. So dou S by dou P at T. You know what to do. Here, denominator there is a P, so on the numerator there should be some term with V. Here in the numerator there is a term with S, there should be the conjugated term T on the denominator. So you write dou V, dou T, okay, and even you can write what should be constant. The constant should be the conjugated term of V. Okay, numerator's conjugate term should be there in the denominator, so it should be P. Now one more thing finally, that is very important. You have to predict what will be the sign of this quantity. See, check whether do you have P and T on the same side in numerator and denominator? No. Here it is P and S. Here it is V and T. So this term must be bearing a negative sign. So this is your, I think it was your fourth Maxwell equation. The fourth Maxwell equation as per, okay, even though, okay, the naming is not so standard, this is usually, it is called as the fourth Maxwell equation. So by fourth Maxwell equation, or by the Maxwell equation, that's enough. Okay, the numbers doesn't matter much. Fourth Maxwell relation. Okay, better Maxwell relation. Maxwell's equations are usually the terminology that is commonly used with electrodynamics equations. I mentioned about that one earlier. So this term will be minus, instead of plus, minus. T is there, and instead of dou S by dou Pt, I'll be writing dou V by dou T at constant pressure times dP. So the left side is once again TdS, right? Now look at the expression. Is it enough? Yeah. Right side is Cp. Cp is an experimentally measurable quantity. dt is okay, measurable. Change in temperature is measurable. Change in pressure is measurable. Temperature is even measurable. Okay. So we can see that finally we have reached the equation that we were searching for. This is nothing but your second TdS equation in thermodynamics. Okay, so you can just box it. Boxing any equation, what we mean is that you memorize it if you can. It'll be helping you. Okay, that's there. So we are done. Okay, let me do one thing. Since you have to memorize both the equations, let me write both the TdS equation together. So that is TdS is equal to the first TdS equation we have derived. That will help you to compare and recall it easily. TdS equal to, can you recall it? It was CV dt. CV dt. Then instead of minus, there was plus. If you do the derivation, that is a benefit. You may remember the steps and you may remember the final equation. Okay, so it was again T into, it's quite easy actually if you think of what we have done, what was the motivation. T into, instead of dou V, what should be there? Dou V, it was dou P. Okay, dou P by dou T. When it is dou P by dou T, you know what should come down next. It should be the, what do you say, the conjugate of numerator, that is V. And see, here it is dP, so here it should be what? dV, right? So this one was your, what you call, first TdS equations, right? So both of these equations are looking similar. You can see that how can you go from one equation to the other? The thing is that wherever you see V, you replace with the P, and vice versa. And one is bearing a negative sign. The negative sign for the equation in terms of P. If you remember it, I think just by the time you'll be able to memorize this equation. Please write and practice, do the derivation. These equations are quite relevant. And as I told you, since our syllabus do not mention about the third TdS equation, I leave it as an assignment for you to check how to obtain the third TdS equation. And to support you, I have already uploaded one article on the derivation of the third TdS equation also in additional reading materials. That's only for just for your practice, and also to take you beyond the barriers of the syllabus. Okay, practice it. So I just conclude this session here. Remember, we are left with two more applications of Maxwell's relations. There are several applications, and your syllabus is giving you some samples. Okay, so of which we have discussed the application in terms of TdS equation, and we have discussed the first TdS equation and the second TdS equation. So this is the equation that we have discussed. I think you can just see that this is the first equation and this is the second equation. Only one thing is that the Cp dt term has been written second, so that is why there is a negative sign here. Okay, and the Cv dt term also has been written as a second. Okay, and this is a third TdS equation which we didn't derive, which I have told you to just try to derive it. Okay, there are some applications of this TdS equation also that is mentioned in your notes, which already I have uploaded. Please refer to the applications of TdS equations. So it's just like a chain. TdS equation was derived by using Maxwell relations as an application, and TdS equation, there are two TdS equations, and there are separate application of each of this TdS equation. Some examples have been mentioned in your notes and in your reference textbook. Please refer to that. It's easily comprehensible, because there is nothing new there. There is no new concepts there. If you have any doubt, feel free to contact me. I can devote some time on it. I'm not doing it here in the online class because already there is too much of digital material for you. Please, just if you face any problem, I will be at your service. You can just give me a text, a message. I will do that, and I will present it. Okay, so I hope that this session was useful to you. Thank you.